Okay, given this point, 12, 1, negative 5, do you see it in the room?
Oh, it's over there.
It's about 12 feet this way, about 5 feet this way, and about 1 foot up. Does that kind of match up? I know, fucking rounding here. This isn't perfect, but okay. So that's about that point. So then the question is, if this was going 4 units in the x direction each second, like you were to like film it and you could see, oh, I can tell it went 4 meters in 1 second, then it would be going 4. Then how would you write that as I just told you a starting point and I just told you its direction? Write it as a vector equation. You got the starting point, you got the direction it's going. Don't overthink this, it's pretty easy. I'll pause for a second while you give that a shot. Maybe that'll get you going. How about x, y, z equals, yep. Sounds like a sort of relative of a sheep. Lambda. Okay. Lambda. Okay. I agree. 4, 0, 0 because it's only moving in the x direction. And why did you put 4? All right. But why not a 1? Just a second. Would you agree that that's heading in the same direction? Okay. Do you get that if I change this, it's still heading in the same direction, but it's going further for each time I put in a lambda? Do you get how that's related to the speed? This would be going 4 for every lambda. And if we make lambda seconds, which is what we are going to do in the lab, lambda is going to be seconds. Okay. And if we make these meters, that would imply you're going 4 meters per second in the x direction. All right. So when we go and do the lab, do you also get that we're going to have a bowling ball coming, let's say here, and another bowling ball getting launched from over here, and that their paths are not going to be 3-dimensional. At least one of the dimensions is controlled, because why? Because they don't go up and down. It's on the ground. So therefore, if you wanted to have a z, your z would always be 0. It's on the ground. Height off the ground, 0. Okay, always. So anyway, so it's really just 2 dimensions. It's got x and it's got a y, and you get that the bowling balls, if they were like big long lines, they would cross. But the trick is going to be to get them in the same place at the same time. All right. So if we just rolled them straight at each other, this lab would not be difficult. You could just make them hit, okay? But when they're coming at angles, that's what makes it more challenging, okay? Then we are going to be rolling them at different speeds, and that's one of the reasons that I just showed you that other thing, is that you can write the speed. The speed isn't that tough, okay? But what if it wasn't just going in the x direction? Yes, sir. Okay, so let's say it was like this one I was describing that was going at an angle like this. It's going to have x and y components to it. Yes. It's going to be going this kind of a speed and that kind of a speed. And together, those 2 speeds make this kind of the resultant, you know. All right, so good. That's good thinking, that you've got x and y together making this angle. All right, now, my job is challenging here because I need to tell you something about the lab. I can't just say 2 bowling balls, roll them, make them hit. That you don't have enough parameters, right? I need to give you some framework, okay? And I also need to give you a lot of like latitude, you know, to try to solve it your own way, because there is multiple ways. In fact, I just ran into 2 math teachers that did this lab last year, and one of them said, "Oh, you did it that way? I did it a completely different way." And they still did it, and both of them worked. Okay, so there's more than one way to do this, to figure out the answer. But would you agree that the point where they meet is kind of important? All right. So if I took this and made it 2 dimensions and just had x, y, you get how that's more appropriate for the context of this bowling ball lab thing? Okay. Then what if I said I wanted to start at this point, 2, 5, and I wanted it to meet at some place. I wanted it to go through some other point. If I knew what the other point was, that wouldn't be that bad. Let's say I know the other point I want it to hit is 7, 12. But that would be knowing where the 2 balls are going to hit. Okay? But if I did that, would you please tell me, basically I've just told you a starting point and a point it needs to go to. Can you write me the right vector for that? This is the easy one. If it starts at 2, 5 and ends up at 7, 12, what's the vector that would make that work? You can't just slap the 7 and 12 here. You could if you did something else. What could you do? Subtract the other one. There we go. And so really you want a 5 over a 7 then. Raise your hand if you got that one right. Okay, good. So now, what if I don't know the point that I'm going through? What could I call that point? What's a logical choice for where it would meet? Yes, or the simpler, xy. Okay, but if we have an xy at the beginning here, I get why you might not want to use x and y, because we already have an x and a y. All right, so what if I knew I wanted these guys to meet at the point P, T? T's not good because it sounds like time. QP, there we go. That's the point I know I want them to cross at, QP. Could you set up an equation for that? Yeah, you could. It's going to have variables in it. It's okay. You have variables. If you have enough equations, you can solve for them. Let's write the equation. If I don't say the point is 7, 12, if I say the point they're going to meet, I don't know. It's QP. All right, did you catch then that this would have to be Q minus 2 and this would have to be P minus 5? Raise your hand if you had that. Okay, good. Then, if I gave you 2 vectors and I didn't know where they hit, but I know that they hit, you've already had this problem before. You can do that. Okay, you just set up your little system of equations and solve it using parametrics. Okay. So the thing that the bowling ball lab that's important about the bowling ball lab is that you get the big picture of where we're going to be rolling this thing. In the commons, we're going to be rolling it, and it all depends on how you like perspective-wise, how you want to set this up. But if you're standing in the right spot in the commons, the door for the port is going to be like back here somewhere. So the whole port is like behind you when you're looking at this. And these are those doors that go to the outside, kind of go over to Pagel. All right. So we're generally in that area. Okay. And we're going to be rolling the bowling ball from here. We're conveniently choosing to start at 0, 0, just to make at least that part easy. Okay. And we already have a starting point? Yay. And then, judging for what I just told you 2 seconds ago about the speed and how you could write the speed into your vector, then you should be able to write, if you just knew the speed of the bowling ball, we're going to roll the bowling ball this way down the commons, and you can write a vector for that, and then you'll have another vector for this other bowling ball. It would actually be fairly simple if we rolled the other bowling ball straight down and just made them hit, okay? But we're not going to do that. especially because this bowling ball is going to be going faster than this one, which is the slow one. And you're going to be launching that slower bowling ball at an angle like this so that they will hit. Okay, and boom, the one bowling ball will hit the other bowling ball. Now, I've not got very good perspective on this drawing. Otherwise, if it was really going faster and had to travel that far, it wouldn't really work. But you're going to have two bowling balls. One's going to be rolling just on the x-axis, kind of like that equation I just set up with you a second ago. You'll be measuring the speed of that bowling ball. You'll have another bowling ball measuring from up here, and it's going to be at an angle, some angle, I don't know, we'll call it theta. And you're going to have to figure out how to get those two to be in the same place at the same time. And therefore, you'll be able to find a spot where they hit. Typically, they hit like maybe in here. So you can tell it's not a huge angle, but some angle you're going to need to have to be able to make it hit the other ball. And then the last piece is that some of you are going to be doing a time delay. You let go of the ball 1 second later, and then, factor that into your whole equation. That really isn't that tough of a factor. You just go from a t is your time to a t minus 1 is your time, and solve it with that. Yes? You had a hand up before. No? Okay, good. All right, so I'll be, how about this? Just generally speaking, we can't figure out the angle. That's what you have to figure out. But what can we actually measure out there that would help? Yes, we can measure distances. Which distance would you like to know? Okay, you'd want to know this whole distance here. Why would you want to know that distance? Okay, yep, you could do that to figure out the speed, yes? How about this? If we're starting at this point conveniently at 0, 0, that makes our starting point really clear. What's our starting point up here then? Don't know. It's an x and a y, right? Do you get why you'd need to measure this way to see where you're starting up there? Let's say that this is 40 feet long. Then this point right here, our starting point, is important for that ball. And our starting point isn't 0, 0. It's going to be 40, comma, whatever. Okay? But we have to measure this, and we have it laid out to measure so that we can show you how far over and how far up that other ball starts at. Because you need a starting point for this. All right. So to write its vector, I'll tell you, its vector is going to be x over y equals, you'll have a starting point, plus your time is going to be factored in with your t, and then you'll have to know the rate it goes. And it won't be that bad. You'll have two vectors, you just have to see where they intersect. But there'll be things like figuring out the speed of the bowling ball. Here's a way you can do it with your iPad, and that's what we're going to do today. Do you know that your iPad takes video in frames per second? So if you never have analyzed this, when you actually look at a video, are you probably aware of this, but you aren't actually watching smooth motion? There's little tiny gaps. You just can't see them. So when they take a video of something for 1 second, your iPad took, well, you have to look it up. Let's say it's 40 frames per second. They took 40, let's imagine it was, they took 40 little pictures, okay? And then it just takes, your mind just strings them together when it plays them really fast. And it fills in all the gaps for you. Isn't that kind of cool? Anyway, so we're going to be taking a video with your iPad, and you're going to have to like dig into the video, get in and see, oh, exactly at what frame did it first get off the ramp. And then we'll have a bunch of meter sticks laid out. And then at exactly what number of seconds did it cross the meter stick? How many frames was that, and therefore how many seconds? You know what I'm saying? Yes, sir. Cool. All right. I'm hearing about a new app. I'm going to pause for a second to check into this. Okay, we were investigating an app, and it looks like the app is something that only physics, the teachers in physics got a special code to get their kids, so we do not have that app available to everybody. But anyway, you're going to be recording the ball rolling, and then we're going to be able to tell from that how fast it's going by looking at the video. How many frames it took to go 1 meter, or if you want, we're going to lay out 4 meter sticks. So if you want to divide it by 4, it might give you an average. That'd be an okay way to do it too. All right. Okay, so that's the setup for the lab. Next thing is I want you to work on a problem in class. We're going to do day 9 right here together with a partner in class while I collect some scores. And some kids finished it in class. Awesome. If you don't finish, then this is also part of your homework. Unlike the other one, day 8 you're supposed to do on your own at home, and you're only doing A and B. This one, you're doing the whole thing, and you're doing it with a partner in class right now while I assign groups and get scores for your homework. Okay, so everybody right now, day 9, get it on your iPad, and then I'd like rows 1 and 2 to just mush together about 6 inches apart. You're going to turn sideways. Rows 2 and 3 mush together. 3 and 4 and 5 and 6. Okay, and that's all I have for the video for today.